Now we want to talk about some more theoretical questions, like if we continue this process, subdividing, constructing reflections and all that stuff, in the limit as our time goes to infinity. So we allow ourselves to imagine what would happen if we could continue this forever. Would we have the whole graph of the sine function? Now, you might not consider that an important question, and well, if you're a certain kind of an engineer, it probably doesn't matter. If you're a mathematician, it kind of does matter. If you want to lay a really solid theoretical foundation for a sine function, for the definition of the sine function, it matters. If you just want to use the sine function to model things, it doesn't matter as much, depending on what it is you want to model and just how secure you want to be with your model. Now, you won't understand what that means, but it's kind of worth coming back to this maybe once a year and just thinking about this until it becomes clear to you why it's important, or until it becomes clear to you, and don't let that happen too soon, that it doesn't matter to you, okay? You're not going to get into the theoretical foundations, and that you're always going to be a little insecure, but really you can do quite a bit just by accepting that this is a sine function, and we can graph the sine function. However, this is a good example of things that you encounter later on in mathematics, and it's not a bad idea to think about it now. And you'll see maybe what I mean. And if you keep coming back to this once a year, it'll become increasingly clear to you what I'm talking about. Okay, so what are we doing here? Well, we're dividing the circumference of the circle into arcs, okay? And if we start with the entire circle, draw this horizontal line through the middle, then we've divided the circle into two equal arcs, each arc having an arc length, a distance that you would travel if you followed the arc, that's half of the entire circumference. Then we construct this line perpendicular to this one, and we will have divided everything into we will have divided the entire circumference into four arcs, each arc, four equal arcs, each arc having length 1/4 the circumference, having arc length 1/4 the circumference. Well then, as you see, we can subdivide any of these arcs, again, in getting an arc that's got a length 1/8 that of the circumference. And then we can subdivide each of those, getting 1/16 of the circumference, and so forth. Okay, well, what are we doing? It turns out that we're dividing, well, let's just think about these fractions. We got 1/2 of the arc, then we got 1/4 of the arc, then we got 1/8 of the arc, then we got 1/16 of the arc, and then we're going to have 1/32 of the arc, and we continue to 1/64, 1/128, 1/256, 1/512, 1,024 after 10 steps, and then over 1,000,000 after 20 steps. It's going to take a while to do 20 steps because you're going to have 1,000,000 points around here, and you're not going to have time to do that, and the points would all blend together by the time you got to the 20th step, unless you're using a very fine marker of some sort. Any of those numbers, any of those arcs is a rational number. It's 1/2 to some power. 1/2, 1/2 to the second being 4. 1/8, that's 1/2 to the third. 1/16 is 1/2 to the fourth, and so forth. So we could say that the arcs that we get have lengths 2π/2, 2π/4, 2π/8, 2π/16, etc. It's always 2π/2 to the n, where n is the number of steps that you've taken. If your first step is this horizontal line, your second step is this vertical line, then your third step would be here, and it's pretty clear that now you've divided the circle into 8 parts. 2 to the third is 8, so there's your n equals 3. Okay, so the first division, n equals 1, 2 to the 1 is 2, vertical line. Second division, 2 to the second is 4, then this one, 2 to the third is 8, and the pattern continues. We've established the pattern. We have 2 pi over 2 to the n, an arc length of 2 pi over 2 to the n. If we consider this to be the unit circle with radius 1, okay, so that the circumference of the circle is 2 pi. Okay, well, now, if we do this, if we now consider everything to be on the unit circle, then these are the arc, the lengths of the small arcs, smaller and smaller arcs that we're getting, and any of the bigger arcs that we've marked here is an integer multiple of the smallest arc that we've marked up to that point. So that if we do 2 of these little arcs, well, we get this arc. If we do 3 of the little arcs, we get this one. 4 of the little arcs, 5, 6, 7, 8, and so forth, all the way around. The lengths of those arcs will then be, 2 times that smallest arc, 3 times, 4 times, and so forth. Meaning that any of the arcs that we get here is going to be of what form? Well, first place, these numbers, these arc distances, can all be reduced a little bit because the denominator, well, the numerator always has a 2 in it. We can always divide that into the denominator, and we're going to get what? Pi over 2 to the n minus 1. 2 pi over 2 to the n is pi over 2 to the n minus 1, which is 1 over 2 minus 2 to the n minus 1 times pi. Okay, 1 over 2 to the n minus 1 is 1 over some power of 2. That's a rational number. So we got a rational multiple of pi. However, that rational multiple of pi is itself an irrational number. Now, I'm assuming you know what rational and irrational numbers are, and that you know something about rational and irrational numbers. If you don't, you're going to learn it. And when you come back in a year, you'll understand this a little better. So we have a set of irrational arcs, okay, arcs of irrational length, but they are all rational multiples of pi. All those lengths are rational multiples of pi. We can multiply this arc by any number we want, and we get one of the positions on the circle. Okay? And we can multiply by a number that's even bigger than 2 to the n minus 1, much bigger, because we can continue going around the circle. So we can take this arc as many times as we like. It might take us all the way around the circle. This arc is pi over 16. Okay, the circumference of the circle is 2 pi. So if we do this arc more than 32 times, we're going to be going around the circle again. We can go around the circle again and again. We can extend our curve again and again. And we get valid arc distances, okay? Those arc distances will be of the form p over 2 to the n minus 1 times pi, where p is just the number of times we do the arc. So if we do the arc pi over 16 57 times, then p would be 57. So we'd have 57 over 16 times pi. Okay, so p can be any number. And of course, for some numbers, p, this is going to reduce. For other numbers, it won't. Okay. For even numbers p, this will always reduce. For odd numbers p, it'll never reduce. Okay. Now we identify the arc distance on the unit circle with the angle. That is, if the arc distance is pi over 16, we say that this angle here, the angle between here and here, is pi over 16. Okay, the angle from center out to here. And you should be familiar with radian measure already. That's going to be our radian measure of this angle. Okay, and it doesn't matter how big the circle gets, that's still going to be the radian measure of the angle we get if we divide the circle up into 32 parts. Okay, very convenient measure of angle, and it doesn't depend on how big the circle is ultimately. But radian measure of the angle is always the arc distance that you would travel on a unit circle for that angle. Okay, so now we can say that our points in the circle can be identified with the angular positions p over 2 to the n minus 1 pi radians. Okay, the arcs are p over 2 to the n minus 1 pi. Every arc has to have that form, but every angle then is p over 2 to the n minus 1 pi radians. Now, we don't even have to write the radians when we're talking about angles. We could write the angle as just p over 2 to the n minus 1 pi, because the radian is the default unit for measuring angles. So we don't have to even say radians if our angle is in radians, but often it's very convenient to do that. And often it keeps reminding us of our context. So, radian can be expressed or can be left out. If your angle is anything but radians, you have to write what that unit is. Okay, degrees, revolutions, those are all measures of angle, but you have to write degrees or revolutions if that's what you mean. If you mean radians, you don't have to write it. And if you don't write it, it means radians. So don't write 90 for the angle. That would mean 90 radians, not 90 degrees. Okay. Okay, now, we want to talk about just what this means for the definition of the angle. So we're going to go on with this in another clip.